This video will be solving a pH problem for a weak acid mixture. So a couple of items to cover that make this a little bit different than just regular weak acid pH problems. So here's our problem. We have a mixture of hypochlorous acid and hydrofluoric acid. Our acids are going to be HClO and HF. So a couple of weak acids. And then here are their Ka values here and here. So it says calculate the pH and then calculate the concentration of hypochlorite ions. So we want this amount, the concentration of hypochlorite ions. These are the kind of things you have to consider. So you could kind of think of these problems as ionizing, these weak acids ionizing in order of their Kas. So you could kind of think of the HF is going to go first, is going to ionize first. And then so it's kind of like you could think of them as happening in steps. So the HF will ionize first, and then this one will go ahead and ionize after. Okay, and something happens where it makes this problem much different than the previous ones we've done. So this is I'm going to kind of do these steps, these bullet points with these arrows here. So I'm going to kind of do these steps when I solve this. So the acid with the higher Ka should be calculated first. And then what's going to happen then is, so for the HF, so that's going to do its thing and make the ions, the hydronium and the fluoride ions. Now, and then we're going to run this through an ice table, and we're going to have an equilibrium amount of H here. Now, this ion is in common with this. So this is also going to ionize and do this, plus the ClO minus ions. Okay, so this amount right here is actually in common with this. So they have an ion in common. And what it's going to do is, instead of when we do an ice table for this one secondly, so we'll do this one first, and then second we're going to do this one, and you'll see that this starting amount is not going to be 0 because this one happened first. We're going to think of it as happening first. So this hydronium is actually going to be plugged into the I line of the subsequent acid. And then we'll run this through the ice table, and then we'll get the total amount of H+, which will be divided by the total volume. And we'll assume that this is a mixture, so we're going to assume that, the volumes are going to be the same. So that's how we're going to do this problem. That's what it says here. So the H at equilibrium from the first acid is going to go into the I line of the second acid. And that's called the common ion effect. When there's something there, this one's 0, this one's going to be 0. So it must go to the right, because this times this cannot be 0 for it to be equal to its Ka. So something needs to go over there. But you'll see that when there's something there, it's gonna kind of prevent more stuff going this way because something's already there. So this needs to go up, needs to not be 0. But since this is not 0, it won't go over as much as if this were 0. Okay, so I think it'll make more sense when we do the problem. Okay, so weak acid mixture. So there's a couple of things to consider, and I pointed this out on the previous slide. So first of all, the HF is going to ionize. So this will happen first. Okay, and secondly, we're going to have the HClO plus the hypochlorite ion. And there's actually a third thing that happens. This may play a role for very, very weak acids. So like the second hydrogen for this acid, so if you have like H2S, the Ka2 for this is like, I think it's like 10 to the negative 19th or something. So this could actually play a role in how this one is calculated if we ever come across that acid, and other super, super weak acids like that. Okay, so water is going to make H plus and OH. Okay, and this Ka is 7.2 times 10 to the negative fourth. This Ka is 3.5, so that's why I listed them in order like this. And the Ka for water is around 10 to the negative 16th, I believe, something like that. So this is way too. So this one. So water. This is gonna be way too small to contribute a significant amount of hydronium of H plus. Okay, so this is going to contribute. That should be significant. That's going to be the most significant. In fact, you'll see that this one is so low in comparison that it's probably not even going to affect this number. Actually, I know it's not. This is super low. So this probably will not affect this number, and this is not even close. So this is we're not even going to worry about this process. Okay, if you see the Ka, if you see a Ka around this number, then you would have to probably consider it. Okay, the amount of hydronium added by water. Okay, so remember, what we're trying to do eventually is get the pH, which is the negative log of the concentration of H plus. So this is the total moles of H plus divided by the total volume. Okay, so we have to consider all our contributors of H plus. We have this acid, and water is also a very weak acid. Okay, so let's go ahead and see what happens when we start doing this problem. Okay, and I had this beaker and I was going to draw all these ions in here, but I kind of pointed it out with these dissociation equations so that this one's going to happen the best. Okay, so let's get started on this problem. So the first one was the HF. Okay, so I'll write out my ice table. Okay, this was 1.50. These are zeros because nothing has happened yet. This is the first one to go. Okay, this goes up by x. This goes up by x. Okay, this is 1.50 minus x. Okay, we set it equal to my Ka to the negative fourth equals x squared over 1.50 minus x. We're going to go ahead and assume that this right here is negligible compared to the 1.5, so we'll use the assumption rule. And we'll go ahead and we'll check it out, see if it's valid. So if I times this by 1.5, so x is going to be the square root of 7.2 times 10 to the negative fourth times 1.5. Okay, and for x I get 0.033 molar. So if I want to check this out, I'll do the 5% check. Should work by plenty. So over 1.5, I get 2.2%. So this is okay. So our assumption is okay. So that's the amount of H plus. That's my amount of H plus. And that's my amount of F minus. So we need to, this problem also asks us to calculate the ClO concentration, okay, at equilibrium. So it asks us to calculate that amount also. So now we need to go on and do the next equilibrium. So this is the second acid in our mixture. So we're going to think of this one as happening after. So ClO after the HF. Okay. So we'll set up our ice table, and this was starting amount was 1.50. Okay, now here's where it gets different. Okay, this number is from, so the point, we're going to actually put 0.033 here. And remember, this is from the first ionization. And this is called the common ion effect. You notice if this is not zero, Le Chatelier's principle says it won't go over as much. Okay, to reach Ka. It still needs to reach Ka because the ClO minus was not a common ion. So this one's going to be zero. So it must go over to the right, because, or else our numerator, if it didn't, our numerator. Okay, so since that is 0 initially, this cannot be, it cannot be 0. Okay, so something has to go over there, but you'll see that since something was here, so something is there, that it's going to go over even less than it would have if that were a 0. Okay, over HCLO. Okay, so this is going to go down by x, this goes up by x, and this goes up by x. So we're interested in this number because the problem asked us. It asked us to calculate this amount. Okay, so this is going to be 1.50 minus x, 0.033 plus x, and this is going to be x. Okay, so we take our Ka, which is 3.5 times 10 to the negative 8, and that's going to be equal to 0.033 plus x times x over 1.50 minus x. Okay, so here's where things also get kind of interesting too, is this is so low, okay, I'm going to assume that even though this is pretty low, I'm going to assume that since this is so low, I mean, that's to the negative 8, so that's 7 zeros, and then a 3 and a 5. So that's so low, I'm going to assume that that will not affect the 0.033. Okay, but be careful when you do that, okay, just for future problems. So I'm going to also assume that that is irrelevant compared to the 1.5. Okay, so this reduces my problem, and it makes it much easier now. So I'm going to go rewrite this. 3 times 10 to the negative 8 equals 0.033 times x over 1.5. So this becomes a lot easier to solve. I don't need to graph this or anything. So for x, I get 1.6 times 10 to the negative 6. Okay, and this is my CLO minus concentration. Okay, molar. Now, if you wanted to see, you could do a little check here. So to check our assumptions, we would need to compare x to this number and this number. Okay, so I know x, I know it's not even close to that number. As a matter of fact, it's not even close to that number, but just for fun, we can compare it because sometimes it will affect the number and you'll end up having to graph this part of the problem to solve for x or use the quadratic formula. Okay, so that's not even close to 0.033. That's not even worth plugging in my calculator. So this is going to be way less than 5%. Okay, so that's my answer. I believe this problem also asks us to calculate pH, which is interesting because our H plus is 0.033 plus X, so it's 0.033 molar plus X. So X, again, is this number, so it's going to be our X is and just to drive this message home, I'm going to write it out instead of scientific notation, so it's 1, 2, 3, 4, 5 zeros, and then a 1 and a 6. So we see that this is not, we see that our HCLO ionization is not a significant contributor of H plus. Okay, and then water, we shouldn't even bother with water. Okay, so this is not enough to affect this number. So our pH then is going to be the negative log of 0.033. Okay, and for that I get, so I have 2 sig figs, so my answer should have 2 decimal places. So my answer, I get 1.48 for the pH. Okay, so just to recap the problem again, this is the ion that they had in common, that the two acids, the hydronium that they make. So so we need to plug this in from the first ionization, and then we went in order according to the Ka. So the first Ka, the highest one, happens first, and then the result of that goes into the next equilibrium that's going to happen. Okay, and make sure you check your assumption rules here. and here, okay, especially on this one, because this is from the first ionization. So here's the your turn. So set it up, try to follow the example. I think you'll see that this is set up to be a couple of differences. I think one thing that you want to really consider, it's kind of a hint here, is one thing to consider is take a look at the Ka values. So they're actually really, really close to one another. Okay, so that's gonna actually affect how this problem is done. Okay, so let's see what you guys come up with for that.